Hello everyone. In this video we're going to go over section 10.1 class node problems. So first we have a graph below and we want to classify each of the walks that we have as specifically as possible, and then we're just going to justify the answer. So the first walk is just going to be 1 2, then 2 3, then 3 1. So pretty much we're going 1 to 2, 2 to 3, 3 to 1. So in that case, all edges is this, no edge is being repeated, and no vertex is being repeated except the vertex number 1, which is the start and the endpoint. So this is going to make it a simple circuit. So these are conditions for a simple circuit. Okay, so no edge repeated. Okay, so this is terrible for writing here. Simple circuit. Promise in the solution I'll type this and so it will look more better. It will look better. Now for B, we have that we're going from 1 to 2, 2 to 4, 4 to 5, 3 to 1. So 1 to 2, 2 to 4, 4 to 5, 5 to 3, and 3 to 1. So as you can see, we're pretty much covering all the edges that we have over those assists. No edge or interior vertex is going to be repeated, and the walk is visiting all the vertex exactly 1 before returning. So this is what we call a Hamiltonian circuit. And so once again, all edges is no repeated edge or vertex, no repeated edge or vertex. And visit all the nodes. So those are the conditions for the Hamiltonian circuit. Now, next we have 2 1 3 5 2. So 2 1, and then go to 3, and then go to 5, and then go to 2. So we're doing this 2 1 3 5 2. Now all the edges that we mentioned exist, and we have no repeated edges or interior vertices. So we're going to have that this is another simple circuit. Okay. Now last, we have 4 2 5 4. So from 4 we go to 2, we go to 5, we go to 4. So we're going over this triangle here. So once again, all edges is here, and we're not repeating edges or interior vertices. So this is a simple circuit once again. So this is just classification of the walks. Okay. In question number 2, we have degree sequences. And with the degree sequences, we want to determine whether a connected graph with those degrees could have an Euler circuit, an Euler trail, but maybe not a circuit, or neither. And then justify by using the Euler circuit theorem or the Euler trail criterion. So the first, we have this sequence here with degrees is 2, 4, 2, 4, 2. So here, all the degrees are even, right? And so by Euler circuit theorem, a connected graph will have a Euler circuit. A connected graph will have a Euler circuit. Now we get degrees 3, 2, 3, 4, 2. So we have odd degree vertices. We have 2 degrees, 2 vertices with degree 3. And there are exactly 2 odd degree vertices with those. So by the Euler trail criterion, this graph is going to have a Euler trail. So Euler trail. This graph has a Euler trail, but not a circuit. Okay. Now, the trail must start and end at 3. Otherwise, it's not going to work out. Now, for question 3, we have a sequence of degree 3, 3, 4, 4, and 4. So once again, we have 2 odd degrees. And we're in a similar situation as we were before. We can have, by the Euler-Trailer criterion, this graph has a Euler trail. Okay, Euler trail, and once again, must run between the 2 odd degrees. Let's run over the 2 nodes with odd degrees. That is for getting to have that particular Euler trail. Now, for D, we have once again a situation where we have 2 odd degrees. We have one with degree 1 and one's with degree 3, as you can see here, and the rest are just going to be degree 2. Once again, by the Euler trail criterion, we're going to have a Euler trail. So hopefully with that, this clarifies the notion of the use of the Euler trail and the Euler theorem. The Euler circuit theorem needs all of them to be even. Okay, but the Euler trail is going to allow, by the Euler criterion theorem, is going to allow me to have 2 of those at least with odd degree, but they need to be the starting and finishing parts of that particular trail. Now let's go to question number 3. Okay, now in question 3, what we're going to do is the opposite of what we were doing before. So we're going to have a graph, and we're going to try to come up with a graph that matches the behavior that we have. So here, for each description, either draw a graph satisfying or explain why those graphs cannot exist. So A is a connected graph with 4 vertices that has a Euler circuit. So if we want to have a Euler circuit, one of the things that we need is that it has all the degrees being even. So now, if we want to draw a connected graph on 4 vertices that has a Euler circuit, let's first draw the 4 vertices. And now we need to make a connected graph. So we can make it connect, but it's not going to have either a Euler circuit or a Euler trail, because to connect those 4 vertices, they need to connect in a way that they all have degree 2 or odd. So it would be the best bet would be something like this. And so in this case, everything here has a degree 2, and then it will have a Euler circuit. Now for B, we want to find a connected graph on 5 vertices that has an Euler trail from vertex U to vertex B, but does not have a Euler circuit. Okay, so the easiest way to do Euler trail is, of course, to have 2 vertices that are going to have odd degrees, and the other ones are going to be even. So we can go over something very basic. We can go like 1, 2, 3, 4, and 5. Now we can connect those. So let's connect this with this, this with this, and this with this. So now notice, let's say U, and this is B. Now these are going to have degree 1. So this has degree 1. degree 1, 2, 2, 2, and 1. So by the Euler criterion theorem, this has a Euler trail, or this is a Euler trail. Okay. Now, for C, a connected graph on 4 vertices where every vertex has odd degree. Okay, so this graph with 4 vertices, we can go for something similar to what we had before. And so we can initially connect this. And so in this way, they're going to have 2 degrees as we have from before. But because we want to have odd degree for all, then we can just make an extra connection. So this with this. So now every vertex has odd degree. This has 3, 3, 3, and 3. Now, this has neither Euler circuit or Euler trail. Now let's go to question 4 and 5. So for question number 4, we want to determine which each graph is connected and state the number of components. So from the first one, you see that clearly it's not connected because it's made by 2 separate components, right? And those components are not tied in any way. In contrapositive or in a different direction to that, you can see that the second graph B is actually connected. It doesn't have any disjoint parts, and it has a single component. So this is the difference between a disconnected graph with 2 components and a connected graph with a single component. So for question number 5, for each graph, we want to determine whether there's an Euler circuit. And if there is, then let's exhibit 1. And if not, let's explain which condition is failing. So for the first one, notice that we have that most of this have degree 3. So A has degree 3, B has degree 3, E has degree 3, D has degree 3, and then C has degree 4. So because they don't have all the degrees being even, there's not going to be any Euler circuit. No circuit or trail here. We just have one single, we have 4, we have a degree with, that has, we have one vertex with degree 4, and we have 4 with degree 3s, which is not enough to produce a trail or to apply either the Euler circuit theorem or the Euler criterion theorem. A circuit in general, they can be no Euler circuit. A circuit in general, you can think so. If you can join any, of course, any path that you do like A, B, E, D, A will be a circuit. But that's it. It won't be a Euler circuit. Now, for B, we have that you have B has degree 2, S has degree 2, but you have Q that has degree 3, and you have R that has degree 3. So you have B with 2 degrees, Q with 3, R with 3, and S with 2. A Euler circuit is not going to exist because it doesn't have all the even degrees. No even degrees for all nodes or vertex. Euler trail might exist from Q to R, because you have that they have odd degrees, and the other one are going to be even. So you can create one Euler trail from Q to R by the Euler criterion theorem. All right, so let's continue this in part 2.